acid-base titration. However, unlike the previous video where we looked at a weak acid being titrated by a strong base, in this one we'll look at a weak base already in the solution being titrated with a strong acid. Let's have a look. As you can see over here, this was in the previous video where we had a weak acid in the solution. As you can see, acid was in the solution, then a strong base got added in, and as we can see, it increased in volume down here, right, in the x-axis going to the right, and then eventually caught up to the equivalence point. Equivalence point was higher than a pH of 7. Now in today's video, we're going to be looking when we have a weak base already in the solution, so we could have, base in the solution over here. And then of course we can have here over on the bottom here the volume of the acid added. Right, of course this here is going to be our pH of 14 and pH of 7. Okay, even if you have a weak base, as long as the concentration is high enough, it can still be quite high over here. Okay, so above a 14 or around a 14 up there, quite high of a pH. And then as soon as we start adding the acids, we start going downwards. As you can see, we're starting to go downwards as we add more and more acid, because obviously when we add acid, this decreases the pH, right? So we're just going downwards in the pH. And then at a certain point, we hit this area over here where the acid concentration is half the amount as the base. What does this mean? Acid is extremely strong, right? We're using a strong acid. We're adding a very, very strong acid. So we only need half the amount of acid because this is so powerful, okay? We need a lot of this one that is in the solution right now because it is very weak. So of course this is going to be in plentiful amount of volume, but of course the acid is so powerful, only half the amount is actually needed in order to get to this point over here known as the buffer region. So in case you kind of forgot what the buffer region was, this is where there is equal amounts of the weak base and its conjugate acid. Okay, and obviously these are existing within the solution. So equal amounts of this and equal amounts of this. Obviously we have a very weak base in here. So at this point over here, there is equal amount of both the weak base and its conjugate acid. Then from here, as we continue to go down, because we keep adding more volume of the acid, eventually we're going to get to a point where it hits the equivalence point. The equivalence point is going to be right over there. And as you can see, the equivalence point is below a pH of 7, which is quite different than what we saw in the previous video where the equivalence point was going to be at an 8. So why is this the case? All right, why is the equivalence point so much more below pH level reading marker of 7? Well, we have our base over here, and if it's dissociated within the water, it's dissolving in the water, it's going to end up creating this, because obviously if this here is a base, then this here is going to be the acid. So the acids are donating its protons as hydrogens towards the NH3, so this becomes an NH4. This one loses its positive charge, so now it's a little bit more negative, hence why we have a hydroxide over here. And so now we have this hydroxide just kind of free floating, swimming within this beaker of a solution, making it basic. Okay, so right now we have a basic solution right now. This OH minus is floating around. Now eventually we're just going to kind of bring this down over there. And now this HCl comes in, okay, in order to titrate the solution. So obviously this one here is going to be more acidic. This one here is obviously going to be basic. So once we're adding this HCl, what's going to happen to this equation? As you can see in our product side, this one received a hydrogen, obviously, because this H went over towards the base, because the bases accept the protons, so this becomes a neutral H2O, and then this one lost that H plus, so now it's just Cl alone, and it's a little bit more negative now. Okay, I forgot to put in a little AQ over there. Now, how do we know if we've gotten some sort of neutralization occurring? How do we know this? Well, number one, it's pretty obvious that we see water here. It's very neutral, okay? So this is a key pointing factor that we have been neutralizing quite well. We also know that this Cl minus here is a weak base. So why is this important? If Cl minus is a weak base, this means that we are no longer having an extremely high pH anymore. Obviously, hydroxide is a very, very strong base. Cl minus is not. So we're getting a little bit lower in our pH. Now, how can we prove that this Cl minus is a weak base? Well, where did this Cl minus come from? HCl, let's say if this here is the acid, then this here would be its conjugate base. And we all know HCl is a strong acid. So if this here is a strong acid, its counterpart of its base is going to be a weak one. Now that was dealing with the hydroxide. Okay, how about this NH4 plus? So let's bring this back up here. So let's say this NH4 plus now is also still floating within the water, within the beaker. What is going to happen now? Well, this is already more positive, right? It definitely does not want to get another hydrogen because hydrogen is already positive. It's like a proton. So why would it want another H? Okay, it's obviously not going to happen. So this one is then going to donate that extra proton towards the H2O. So of course, this is not going to have 4 hydrogens anymore. This will only have 3 hydrogens. So this becomes now NH3. Now, how about this one? It received that proton, so now it becomes a hydronium. So this is obviously aqueous. This is going to be aqueous as well. Okay, so we have this and this. Now, the important thing to consider here is that this H3O plus over here is hydronium, which is definition of an acid. Whenever there is a release of hydrogen or formation of hydronium, this is an acid. Okay, so what can we say here? This increase of the hydronium causes the pH to decrease. Okay, so what does this mean about the equivalence point that I've been trying to emphasize over here? So therefore, the equivalence point gets lowered, as illustrated in this graph over here. Now it's saying determine the pH at the equivalence point. Equivalence point means the amount of moles for this one and the amount of moles for this one should be identical, but let's first write out the actual equation. So we have our NH3, all right, and we're going to be adding it with our hydrochloric acid. What's going to happen from now? Of course, this one is going to go towards base because this here is the base. This here is obviously the acid. So this is going to take that. It's going to become NH4 plus. And then this one is going to just become Cl minus. Now let's put these as aqueous, of course. And so now we're going to be just putting our volumes and our moles and concentrations for those. So do we have the volume for our NH3? Yep, it's 50 milliliters. We can just put it in liters really quickly. In terms of our concentration, they do give it to us at 0.150 moles per liter. How about the amount of moles? You could easily find your moles. Just do your C is equal to N over V formula. You can try it right now. Tell me what answer you get. You can get 7.5 times 10 to the negative 3 moles. Okay, how about for our HCl? Well, our HCl, they do not give us a volume. How about for our concentration? They give us 0.150 moles per liter. How about the amount of moles? That's not given to us, but remember they did state that this is at the equivalence point, so these need to be identical. So what would this one be here? This is also going to be 7.5 times 10 to the negative 3. So we could easily use our C is equal to N over V formula, isolate for V. What do you end up getting then? You also get 0.050 liters. Now what are we going to do? Well, once we create our amount of moles, we need to create a nice table just for the moles, all right? So let's create a nice table over here. So I've made it over here. Of course, this is just going to be in moles before we start doing another nice table over here in just moles per liter with concentration. So right now we have this amount of moles of this and this reacting together within the beaker, right? So obviously this one is in here first, and then we eventually added that HCl a little bit later on in order to titrate it. So we have our moles over here. Let's just keep writing it down. 7.5 times 10 to the negative 3. And we have this one also added in at the equivalence point. And then, of course, these are not made just yet, right? These have to react before it creates any of this. And then of course these are going to be used up, so they become negative. So then obviously if these are negative, these are being produced, so then these become positive. This becomes 0, and then this just kind of falls downwards at equilibrium. Alright, so this is what we have for our moles. Now we have to remember that we added these two things together, right? This volume and this volume together. So if we just bring these two volumes down together, our volume total, okay, would just be 0.1 liters. So this 0.1 liters is important because this is going to become now the denominator under this moles over here, so that we can eventually get up the concentration. Okay, so what would the concentration be then? 0.075 moles per liter. Now let's put them all into an ice table. Before we add them into an ice table, we have to quickly figure out whether we're going to be using an equation where it's more acidic approach, or number 2, where it's more basic approach. For an acidic approach, we're just going to get our NH4 plus over here. And we're going to be adding it with the water, because obviously when an acid and a base, these here react, we get a salt and a water. Okay, so if our number 1 is always going to be an acid approach, our number 2 is always going to be a base approach. So if this one acts like an acid, this is going to donate that proton towards this, and then this H2O is going to become an H3O. So then this becomes NH3, and this becomes H3O. So this is our hydronium. Now, how about for our base? Well, if this acts as a base, let's just first quickly write this down just like it is above it, okay? So now it's going to receive this H+, so then it's going to become NH5. Then what happens to this one over here? It lost that H, so now we only have one H, so it becomes hydroxide. Which one are we going to be using? We're going to be using this one, or we're going to be using this one. Let's give it a try right here. Let's add this one over here, down here. And let's do our little ice table using this acid approach. Okay, this is obviously going to be number 1, and obviously we're going to be using moles per liter right now as a disclaimer. Okay, so let's create our little ice table. So we had our concentration on here, which is 0.075, so let's just write that down. This one is all going to be null, and then these of course are just 0 so far. And then for a change, obviously there's no real reaction happening between these two, so we can't be putting a number, but we can just put a vague negative x over here. Obviously we could be putting negative because it's being used up. X is just our variable that we're going to be using, and then of course then these are just going to be the positive versions. Okay, so we just add these up for our E chart. Then this is what you get. Alright, so now what we're going to do is get our Ka or Kb formula. Okay, which one are we going to use? Well, obviously we're dealing with an acid route up here, where we're using number 1, so we should be using a Ka route, not a Kb formula route. So we'll just be using our Ka is equal to our x times x all over our 0.075 minus x. So I know we weren't given our Ka value over here. You should have a chart that represents the different Ka values and the different Kb values provided by your teacher. I'll just let you know right now that the Ka value is going to be 5.6 times 10 to the negative 10. Okay, and it's going to be multiplying this, which is going to be our NH3. It's going to be multiplying this, which is going to be our hydronium, and this is going to be on the bottom, NH4 plus. So we just get x squared all over 0.075 minus x. So of course right here we can just cross multiply, or if you want you could just multiply this side by our 0.075 minus x. So then these cancels out. If you do it on the right side, you obviously just got to do it on the left side, so you just multiply that over here. So what do you end up getting now? What do we get? We get our x squared is equal to our 0.075 minus x multiplied by our 5.6 times 10 to the negative 10. So we can just continue to expand over here. What do we end up getting? We'll be putting them all on the left side, so it's easier to put it into our quadratic formula. It's up to you if you want to do that or not. So I'm going to get x squared plus 5.6 times 10 to the negative 10x negative 4.2 times 10 to the negative 11 is equaling 0. So we're just going to be putting this all into our quadratic formula. X is equal to minus b plus or minus the radical. So we get b squared, b squared minus 4 AC all over 2a. So what do we get for x value? If you do the math, you end up getting x is equal to 6.48. 0.46 times 10 to the negative 6. Let's put this all back up here into our pH is equal to negative log of whatever the concentration is. So this here is obviously going to be our concentration. End up getting a pH of 5.19. That's the answer. We have some hydrazine or N2H4. What are we adding it with? We're adding it with this acid over here, hydrobromic acid. And then obviously we're going to be getting this one over here, which is going to be our base, giving that one the H. So that becomes N2H5. A little bit more positive now as a cation, and then of course it lost that, so it becomes Br minus. Now what's going to happen over here? Well, we have to consider our moles and our concentrations and our volumes like always, so let's give that a try. So in terms of our volumes for our N2H4, what do we end up getting? We get 60 milliliters, which would just be 0.06. How about for our concentration? We just get 0.1 moles per liter. For moles, just do your C equals to N over V formula. What do you end up getting? 6 times 10 to the negative 3. For our HBr over here, our volume is going to be unknown. For our concentration, it's going to be 0.2 moles per liter. And of course, for the moles, has it hit the equivalence point? Yep, it's titrated to the equivalence point. So we just do the same value over here. So we could easily find our V. What does our V end up becoming? If you just isolate it for in the formula of C is equal to N over V, so the volume has to be 0.03 liters. Now that we have that sorted out, we can be putting this into our ice table. Again, we're only going to be focusing on the moles within our first ice table. So we've made our little ice table over here. We're just going to get these values that we have. Obviously, this is going to be used up initially. This is going to be used up initially. These are just 0 because they haven't reacted yet. Once they react, what's going to happen? Well, obviously, this is all being used up in conjunction with this one, all being used up, and they're being mixed together to titrate, and they're going to be neutralizing. And then obviously with this is what is created. So we have to give them a positive symbol. This ends up becoming 0, and then this just kind of carries downwards. So now what do we end up doing? Well, we have to remember that we put these two volumes together, right? So what is our volume total of our 0.06 plus our 0.03? What does that end up giving us for our volume? It's 0.09. So this is 0.09 liters, and then these are the moles over here. We just have to be putting them on top of each other, right? So we get our 6 times 10 to the negative 3 moles is going to be divided by our 0.09 liters. This here is going to be our concentration. Now we can do our second ice table. Let's do our second ice table up here. But what are we going to use? Are we going to use the formula equation for an acid route or a base route? Remember, we always do the acid route on the first one, and then we do our base route on the second one. Remember, we have this kind of floating around, right? So we have this N2H5 plus, and obviously there is water within the solution. I'm going to do that down here as well. So which one do you want to use? Well, if this one, and we correspond this as an acid, is going to be removing that proton, so this becomes a hydronium. So we get one less, okay, over here, and one more hydrogen over here. How about this one? Well, if this one acts like a base, it's going to take that over here, so it's going to become N2H6. And this has one less, so it's just going to be a hydroxide. So which one are we going to use? What are we titrating it with? Well, we are titrating this with this, right? We're adding our acid into our base within the beaker. So if we're adding it and we're going to be bringing our acid, so we're titrating with the acid, we should be using the acid formula. So of course, we're going to be now putting this up here in our little ice table. Remember the concentration that we got, right, for this one, N2H5, was 6 times 10 to the negative 3 divided by 0.09 liters. So what was that? It's 0.067 moles per liter. So let's put that over here. Remember, we're dealing with moles per liter now in our second ice table. It's going to be 0.067 right over here. And then, of course, these are null. And, of course, we don't have any of these just yet. Again, it's nothing going to be really reacting, but we know that this is going to be our negative x. These become our positive x, so you just get 0.067 minus x. This becomes x, this becomes x, so let's bring this down over here. So we get our Ka, or do we get our Kb? Well, we're dealing with an acid, okay, because we dealt it with the acid route in our ice table, so it's going to be our Ka, not our Kb. So it's going to be Ka is equal to whatever this is, our N2H4 multiplied by our H3O divided by our N2H5. So what do we get? We get x times x all over 0.067 minus x. Do we have a Ka value? Yep, Ka value, as written in the question, is 7.94 times 10 to the negative 9. So it's going to be is equal to, let that make it more clear, x squared all over, or 0.067 minus x. So of course you can either cross multiply, or what's even easier than that, you just multiply this side over here, right, to isolate for x squared by our 0.067 minus x, so that these cancel out. If you do it on the right side, you got to do it on the left side. So what do you end up getting for our x squared? 0.067 minus x times our 7.94 times 10 to the negative 9. Well, let's just expand it, so we end up getting 5.32 times 10 to the negative 10 minus our 7.94 times 10 to the negative 9. X is equal to our x squared. I'm just going to be putting them all on the left side for ease. For the quadratic formula, it's up to you if you want to do it that way. So we got x squared plus 7.9 times 10 to the negative 9x minus 5.32 times 10 to the negative 10 is equal to 0. So let's put it all into our quadratic formula. So x is equal to our minus b plus or minus radical. Then we get our b squared minus 4ac all over times 1. Let's bring it up here now. You should get a value of x is equal to 2.31 times 10 to the negative 5, whichever one works, right? The plus or the minus route. So the correct route will give you this one. And then this obviously is our concentration, right? This is always going to be our concentration. So we're just going to be putting this into our pH formula, which is negative log of whatever concentration it is, right? So we're going to be just putting this And over here, what do we end up getting? 4.64. This is your answer. These two are the green questions of the day. This is the first one, this is the second one. Please pause the video, try these yourself, and I'll be giving you the answers shortly. This is the answer to the first question. I'll slowly scroll down. And this is the answer to the second question.